Yeah, so next week is Thanksgiving week, and I was excited to find out that for the first time in 160 years, this school is declaring Wednesday off. Right. No, they didn't. Because I remember I was like focusing on how am I going to, because I always somehow teach intro stat on the day before Thanksgiving. And that class will be totally like less than half would come. So, and I didn't want to cancel class. So I would actually record the class and I'm just so glad that the college finally realized, faced reality and just said, okay, right. But we will have a class on Tuesday, though, right? We will have class on Tuesday, and then then we'll be off. Okay, I wanna. Yeah, we don't do that anymore, right? We start classes
I
now.
thought last year was the first year we had Wednesday off.
Are you absolutely sure?
Almost positive.
Because I remember I had to record the class and tell the students if you can come, come. If you cannot come, then
I know my freshman year for sure we had Wednesday off.
yeah. Well,
But maybe I'm crazy.
okay.
I feel like November just I always like block it for my mind. Well, yeah, because it was like Halloween and then all of a sudden it's like end of November. I'm just like, there's too many things to do right now. Actually.
Okay, I want to introduce what motivates group work 33. So group work 33 is the ramp up to where we are going now. So I wanted to warm us up with likelihood again, because I'm going to introduce yet another way to construct tests. Right. And it is, I believe, I might be wrong, but I believe these were inspired by the I almost said Newton-Raphson. I believe this class of tests are called likelihood ratio tests, and I believe they were inspired by the Neyman-Pearson lemma. I can't prove it, but I think it was. I'm quite sure this came after the Neyman-Pearson lemma because it is inspired by that. It is a ratio of likelihoods, which you should be quite familiar with. It's just that it's slightly different. You form this ratio lambda. Now, do you understand the statement? What's max theta bold element of omega, little omega, over max theta bold element of capital omega? Okay, what is capital omega and what is little omega? Look at the notation in equation 651. We are still interested to test things like this. The null says that your parameters are in some restricted set. Again, this textbook likes things very generic, but I will try to translate this to something that you can see. This just means the null says that the parameter of interest, and in this case, we're going to be dealing with mu. Mu is a member of a smaller subset than everything it could possibly be. Omega, capital omega, is the everything in what we call the terminology is the parameter space. Omega capital, uppercase omega, is the entire parameter space. Little omega, as its name suggests, is a subset of that. So what the null is saying is, okay, your parameter is actually a member of a subset of the parameter space versus the alternative which says, no, your parameter is not there. It is in somewhere outside that small thing. Do you understand the two statements? So omega, capital omega covers every possible number. Little omega is a subset of that. And so what this is actually saying is the alternative is saying, no, your parameter isn't where the null says it is. It's somewhere else in the opposite set. So what does the test entail? The test is basically set up a ratio like 6.5.2, where you find the maximizer of the likelihood under the constraint that this is here. And that is why we encourage in this class, and everyone started doing this, always put in subscripts what the truth is. Remember when you did all those type 1, type 2 errors, you wrote a little bit, mu is actually what? That's what this means. It means under the condition that theta is here, what maximizes the likelihood? Versus under the condition that theta is here, what maximizes the likelihood? Now, I'm going to ask you guys, I shouldn't say you guys, okay, but you all, okay? So I'm going to ask you all, I'm going to ask you all a question. Okay, ask you all a question. Is it clear to you that lambda cannot exceed 1? Why is that true? Anyone care to explain? Why can lambda not be more than 1? It can be 1, but it cannot be more than 1.
Yes or no? Almost. So it's like, if you think of it as kind of like a probability, it's like P and 1 minus P.
Okay.
At least like this is the way my brain's
Yes.
going with it. It's like it's a P and a 1 minus P, and then it becomes like that can't be.
Okay. That we are very warm. Can you refine that? I'll give you a hint. Look at the word max. How can you explain to someone who doesn't know statistics why this lambda statistic cannot exceed 1? Is it clear from the notation why this is true? Even not knowing anything about likelihoods or even statistics or probability, why does it make sense that this ratio cannot exceed 1? The highest it can be is 1. What's little omega and what's big omega? Right? Look at the max, look at little omega, and look at big omega. What is it telling you? Right? It's saying something to you. What is it saying?
Oh,
Yeah.
is it because little omega is a subset of omega?
Yes. That's why you need to go to 331 is to think this way. When you maximize over a larger set, don't you have more candidates? All right. When you maximize over a smaller set, isn't the smaller set in the larger set? So it's like, if you look at a sea of 100 people and ask who's the tallest here, and then now I have a subset of the 100 people, and it's only 5 people, who's the tallest here? Can the tallest person in the 5 be taller than the one in 100? No. And therefore, that's a very important thing. This ratio cannot exceed 1. And so how do you construct a LRT, a likelihood ratio test? You make an LRT has a very nice meaning in Malaysia, not here. Everyone calls the Chicago train the L. We call it the elevated rail. But in Malaysia, we call it the light rail transit. It's light because it's the number of passengers can sit in it. So we have an LRT system. So, well, anyway, so every time I see LRT, I think of the train. But anyway, so the LRT test is this: reject null if capital lambda is less than some c. Is it intuitive why you should reject the null if lambda is small? Is it intuitive? What does lambda measure? The maximization of the likelihood under the null statement of where the parameter is. If this ratio is very small, shouldn't you throw the null away? Is the null doing a good job maximizing the likelihood? No, it's small. And so the rationale for the likelihood ratio test is go set up this ratio like the NP lemma was a ratio. Set up this ratio and say, I'm going to reject the null if this happens. And how do you find out what C is? That's the second part of the problem. You need to know the probabilistic nature of lambda, just like what you did with all the Newman-Pearson lemma, and find the K. Remember that? Now it's C. Okay. K star. Oh, okay.
Okay, so like
So in other words, again, the likelihood ratio test gives you a recipe and then walks away. It just says, here's a reasonable way to test. Form the likelihood ratios of the maximized likelihood under all parameter values specified by the null, whose candidate maximizes that likelihood. You divide by, if I had no constraints, what is the maximum likelihood, period, over every possible value? Find this ratio. If this ratio is small and unsatisfactory, I'm going to reject the null. Does this make sense as a testing regimen or a testing recommendation? I said yes. In other words, the null is not doing a good job maximizing the likelihood. The thing you have proposed under the null is not good. It does not maximize the likelihood to my satisfaction. I'm able to find higher values of the likelihood outside the null thing. That's why reject null when lambda small. Now, how do you specifically find this C? This is exactly parallel to the problems you have done, or how did you find K star? You say, okay, I want probability of reject null when null true to be 0.05, something like that. Then now we use normal tables because the statistic of choice had a normal distribution and you could find the K star. That's why we did all those group works. We are going to do the same thing here, but now for likelihood ratio test. Now I built up this bubble. Now the bubble is going to burst. Is a likelihood ratio test UMP? Is it uniformly most powerful? There is no guarantee. I love that question because I don't know whether you realize it's not easy to generate umps. Only in very forgiving, unrealistic situations can we say that a test adheres to the Neyman-Pearson condition and is therefore ump. Not even. So, and the word is this, likelihood ratio tests, the word most powerful doesn't even enter the dictionary because you are always testing against composite hypotheses. We are moving away from those simple versus simple kind of scenario. If you remember, the foundation of the Neyman-Pearson lemma is you are testing simple versus simple. Likelihood ratio tests to answer, I've not answered Anya's question, why use it? Likelihood ratio tests are to answer a plethora of questions where you do not have simple versus simple, you have composite versus composite, all kinds of bad things. And it's just, in other words, there is no guarantee of optimality. It is a reasonable thing to do. Am I making sense? But I am not guaranteeing it's UMP or anything. UMP tests exist in very specific things like that. This was inspired by the Neyman-Pearson lemma, but it is not optimal. It is a reasonable thing to do. That has to be gotten across, right?
Is it useful too for simple versus composite?
Yes, and the first group work we are going to do to implement this is a simple versus composite. Yes, but do you realize I never said that little omega has to be just one number? Do you agree? See? And that's why real analysis is difficult. We tacitly assume, ooh, what's a subset of? Let me ask you this: the real line could be capital omega. Okay, capital omega could be every number on the real line. Can you name me some possibilities for little omega? If capital omega is the whole real line, all possible values of mu, for example, can you give me some suggestions of what little omega could be? What's a subset of the real line? What kind of question is it? It's so many. A number, two numbers, half the real line. So again, to answer Anya's question, all this becomes moot because the test is extremely generic. It just means you give me a subsetted parameter space called little omega, which can be as easy or as hard as you want, just that it is a subset. It could be half the real line versus the whole real line. I'm so glad we're having this discussion, and I can see the lights going off, no, not going off, switching on. Switching on. The alarms go off, lights go on. Okay. And all that. And that is why this will give me the chance to tell, do you see here something we have never done yet? We've always set alpha to be the probability of rejecting null for one value of the truth, and that one value of the truth was a singular value, mu equals 10 or mu equals 15. Do you realize that this is even more generic? Alpha is actually the significance level of a test is actually more complicated than what you've been doing. It worked out in all the cases so far because every null hypothesis we've dealt with is always just one number. But actually, the definition of alpha is deeper than that. It is when I travel in my entire space specified by the null, the maximum value of this property, that's actually the significance level of a test. I don't know whether this is getting across to you. You see, that's why teaching hypothesis testing is challenging. Because there are so many, it's like a scaffold. You have to learn the simple stuff first and then try to generalize. When you do a simple versus simple, that's when life is, when you're a baby, you have no worries. You don't even know what worry is, right? So simple versus simple is the easiest. One singular value versus one singular value. We've now expanded that to UMP, where you have simple versus composite. That's still okay, because evaluating alpha when your null hypothesis only specifies one number is not, it's a walk in the park. It's that number. When you maximize, if you are one person in the room, who's the tallest in the room? You. So the max word is not required when your null hypothesis set, the little omega is really small, one number. But you must understand that in the real world, people test all kinds of things. You can also have a composite null hypothesis. And if that's the case, the significance level of the test is you need to search as you travel in the entire null hypothesis specified space, who is going to maximize the probability of rejecting the null. And that's your significance level of the test. Right? This is a very deep point, and if you don't get it immediately, you can come ask me about this. It's a point that confused me as an undergrad as well, because it was not taught to me in a scaffolding way. As I said, I did not see the distinction between simple, composite, composite. You have to think it's very deep. The topic of hypothesis testing is not the easiest thing to grasp. But I think you all are beginning to get it. And that's basically it. So let me now pass out. Let me pass out. Okay. Let me give out, right? This one. And I want you to follow the instructions. Look word 34, right? Just follow the instructions and I'll help you. All right.